Matrix multiplication is quite a bit more sophisticated than matrix addition and subtraction. And to motivate matrix multiplication, we have an example here of a community college and university tuitions for each year and the way that a student might lay out the hours that they take at each institution in years 1, 2, 3, and 4. So we can see that at ACC, we have in-district versus out-of-district makes a difference, and then out-of-state also makes a difference. But at UT, being in an ACC district versus not being in an ACC district makes no difference. So those are both $500, but there is an out-of-state increase in tuition. And by the way, these numbers are not perfectly accurate for a couple of reasons. One is that they're probably a few years out of date, but another is that the actual tuition calculations are not linear at UT. They don't charge twice as much to take 10 hours as they would to take 5 hours, for example. But this is a rough approximation that at least works for the purposes of illustrating matrix multiplication. What we're going to look at here is using information from both of these matrices without getting into the details of matrix multiplication yet, just to calculate the total tuition for a semester in year 3 for a student who is in the ACC district. So looking at year 3 in this matrix, we see that that student would take 6 hours at ACC and 9 hours at UT. And if the student is in the ACC district, then we're only interested in this row of our first matrix. So thinking about what that calculation would be, we have 6 hours at ACC. Each of those ACC hours costs $60. Then we also have 9 hours at UT. Each of those 9 UT hours costs $500. And so when we put that together, we have 360 plus 4,500, which comes out to be 4,860. So we're looking at tuition of about $4,860 per semester in year 3, assuming that in year 3 we're doing this distribution of hours at the 2 different institutions. So we can see that to do one computation, we used a whole row of one matrix and we used a whole column of the other matrix. This idea is going to stay with us as we get into matrix multiplication. To multiply 2 matrices, what we do is we put together every possible combination of a row from the first matrix and a column from the second. So we'll fill in a table that looks something like this. Our 4,860 was for year 3 and in the ACC district, so we already have this entry right here. We're going to do similar computations to fill in this whole table. I'll get started with one more of them right now, and then I'll pause the video, or I'll let you pause the video and try to fill in all of them, and then you can compare yours to mine and see if we did the same computations. So looking at, let's take, for example, just years 1 and 2 out of ACC district. So we'll fill in this box right here. In years 1 and 2, I have 15 hours all at ACC, so that's going to be 15. And I'm not in the ACC district, so that means that my cost per hour at ACC is $200. So this is going to come out to be $3,000. So in year 3, you're going to have contributions from both ACC and UT. In years 1 and 2, you're only going to have contributions from ACC because the number of UT hours is 0. And in year 4, you're going to have contributions only from UT because your ACC hours are 0. So go ahead and pause the video now and just try filling in all of the boxes, and you can compare to what I have afterwards. To make this a little easier to follow, I did all of my computations for the first column in this brown color. I did all of my computations for the second column over here where we have a sum of two pieces, and I did all of my computations for the third column, for which there were really only two, since out of district and in district didn't make any difference for UT in this midnight blue color. So this is matrix multiplication, and we're going to build it up in a more abstract context next. The first and simplest case is a row matrix. A row matrix is a matrix with only one row, multiplied by what we'd call a column matrix, which is a matrix with only one column. The result of this is a 1 by 1 matrix. So a 1 by 1 matrix is really just a single number. This is like when we answered the first question of year 3 in ACC district. What would our tuition be? Taking a single row and a single column and combining them. What we do is we make sure that they match. We have 3 entries in the first row. We have 3 entries in this column matrix. So we do have the right number of entries for them to pair off. I'm going to take 3 from the first, multiply it by 1 from the second. I am going to take the next entry, which is negative 6 in the first, multiply it by negative 4 in the second, and I'm going to pair off the last entries also, which is negative 2 in the first and positive 7 in the second. And I'm going to add these all together. This is how it becomes just a 1 by 1, is that these 3 terms get added, just like we added together the tuition amounts in our last example. So this becomes 3 plus a positive 24 plus a negative 14, which comes out to be just 13. So the product of a row and a column in that order is a 1 by 1 matrix. When we have larger matrices that we multiply together, we'll do several computations of this type. So the general rule for multiplying matrices is not that they need to have the same dimensions as each other, but that if we write out the dimensions m by n of the first one and n by k of the second one, these n's on the inside need to match. That's what allows us to do the pairing off that we did in this previous example. And our result is going to have the outer dimensions. So we lose the n, and our result matrix is of dimensions m by k. So for example, looking at this first product, we have a 1 by 3. So this is where it starts to become really important to write our dimensions correctly, right? Number of rows first, number of columns second, always. So this is a 1 by 3 multiplied by a 3 by 2. The first thing we check is that it is possible. The 3's match, so that's good. Then we know that our result matrix is going to have dimensions 1 by 2. It seems kind of strange at first, but your result matrix can absolutely have dimensions that are not the same as the dimensions of either of the matrices that went into it. So I'll get ready to make a 1 by 2 matrix. I'm going to allow a lot of space horizontally because I tend to write out long expressions, sort of like this one here, for each computation. So I'll leave lots of room for those computations, but I know it's not going to be a tall matrix. It's only going to have one row. And then here's how I find each entry. I say if I'm starting in, so I'm starting here in row 1, column 1 of my result. To get that entry, I need to take row 1 of the first matrix and multiply it by column 1 of the second matrix. So that computation is going to be now of the type that I did above with the pairing off of numbers. -5 times +1 is -5. 0 times 3 is 0. 2 times -7 is -14. So that's that entry in this matrix. Now, in order to get my next entry, that's going to be right here. So what I'm looking at is row 1. There's only one row in this result, so everything's coming from row 1. But this is row 1, column 2 of my result matrix. So I multiply row 1 of the first by column 2 of the second to get the result that goes in row 1, column 2. So -5 times 0 is 0. 0 times -6 is 0. 2 times 4 is 8. And that's my whole matrix, but I'm going to simplify it and get -19 and then 8. Just a little space between these is all we need to separate them. So that's my 1/2 result. As a little summary of what I was describing while I went through this, we could say that row I of the first matrix times column J of the second matrix goes into the entry in position I, J of the result matrix. It's always a row of the first matrix and a column of the second matrix. We never do that in another order. We never take a column of the first matrix and multiply it by a row of the second matrix. And for that matter, we never multiply a row by a row or a column by a column. I recommend you pause the video for a moment and try these ones on your own to see if you can figure it out. And if you can't, then you'll know exactly where you got stuck and be ready for my solutions. In just a second, I'll go ahead and start filling them in. So we're starting with a 2×2 multiplied by a 2×4. This is possible because the 2's on the inside match, and my result should be a 2×4 matrix. So I will get ready to draw something that's 2 rows high, and I'm going to start with row 1 of the first matrix times column 1 of the second matrix. And for that, I get 2 times -6, which is -12, plus -1 times -5, which is +5. I'll write this out as -12 plus 5. And we will write out the matrix one more time. Then I can go to row 2 of the first matrix times column 1 of the second matrix, and I get 5 times -6 is -30, and 9 times -5 is -45, so that's going to end up being -75 when we redraw this. Next, I will go on to row 1 of the first matrix times column 2 of the second matrix. That goes in row 1, column 2 of my result. 2 times 0 is 0. -1 times 7 is -7. So that's going to be 0 minus 7. I'll finish following this same pattern here. On the next entry down, I get 5 times 0 is 0. 9 times 7 is 63. And working my way to the right, 2 times 1 is 2. -1 times -4 is +4. Then 5 times 1 is 5. 9 times -4 is -36. 5 times 8 is 40. 9 times 0 is 0. 5, let's see, I had that one in the wrong entry. I just moved it real quick. 2 times 8 is 16, plus negative 1 times 0 is 0. So 16 plus 0 goes at the top here. And combining those terms, I get this matrix here, a 2 by 4 matrix. Looking at the next one, I have a 2 by 4, remember number of rows first, number of columns second, multiplied by a 2 by 2. When I check the inner dimensions on this, they don't match, and therefore this is not possible. Even though it would work if I were to swap the order of these matrices, that would give me what I had above. That's not how matrix multiplication is defined. And so as written, we would just say that this is not possible, and then we would stop. So that brings us to our last question, which is matrix multiplication commutative? If you remember back to when you first saw this word commutative somewhere in an algebra class, it means that you could swap the order and it doesn't change anything. Like, for example, 5 plus 2 is equal to 2 plus 5. Changing the order of addition with numbers does not change the result. And with the multiplication of numbers, it also works. 7 times 3 is equal to 3 times 7. We can see with matrix multiplication, the first one was exactly the same as the second one, except for the order, and our result was definitely not the same. One of them is possible and one of them is not. Even if both are possible, they might not both have the same dimensions, and they, in most cases, will not be the same result. So this is a big emphatic no.